So our first speaker, Inna Kompan, works for the German Cancer Research Center in Heidelberg, and she's a member of a CIPI, so that's the open source initiative for perfusion imaging, and it's perfusion imaging that she's going to talk a little about today. So the title of her talk is the implementation of parametric DICOM for perfusion. So Inna, please take it away.
Can you see my slides?
Yes, we do.
All right. Then I'm going to get started. So yeah, welcome. Good morning. Very early morning in my case. Welcome to my talk about the implementation of DICOM parametric maps for perfusion MRI. I have no conflicts of interest regarding this presentation. Okay, let's give you some background and motivation first. So in MR perfusion imaging, parametric maps are usually generated according to the following procedure. So first, a dynamic image series is acquired, and potentially some post-processing steps are applied, and then an analysis is applied on a voxel-by-voxel base, yielding a parametric map. The parameters represented in these maps are, for example, physiological parameters such as the volume transfer constant K-trans and the blood plasma volume fraction VP, but also curve descriptive parameters such as the initial area under curve can be parameters of interest. There are plenty of examples of clinical applications in the field of oncology and neurology where it has been shown that parametric maps hold a great potential to distinguish between healthy tissue and pathologies. But once generated, how does data management of parametric maps look like in research practice? To the best of my knowledge, and I'm happy to be proven wrong there, one of the following scenarios is likely to be the case. So parametric maps are usually stored in commonly used research formats, for example, as NIfTY or NERD files. However, these are formats that focus on the voxel data, however, not so much on the metadata. Metadata being the data needed to describe how these maps were generated from the source data. It is possible to store metadata in these formats. However, as far as I know, this is for most applications not done in a standardized way. These files are then structured in certain folder file naming conventions, as for example can be seen here in this folder. And then along with the actual data, some extra documentation and guideline files are then provided to capture the metadata. Problems arising from these procedures are quite evident. So data handling is error prone and also very group and individual specific. This makes it very hard to aggregate data between different research groups or different clinical sites. And also there might be no information on the source data, so the data based on which these maps were generated, and also patient or study information might be lost. So in summary, I would say good scientific data management is currently lacking in the perfusion MRI community. Instead, a bit of a mess is going on, and it would be nice to clean things up, just make data management more structured and organized. So in order to adhere to good scientific data management, parametric maps should adhere to the so-called FAIR principles. So according to these, first of all, data should be reproducible and reusable. For reproducibility, all relevant metadata should be stored along with the data, making the data self-described. Also, for reproducibility and reusability, these metadata should be richly described with accurate and relevant attributes. Interoperability is defined as the ability to exchange information in an unambiguous way. So in order to exchange parametric maps in an interoperable way, standardized semantics and nomenclatures need to be defined. Also, there should exist an infrastructure to make data findable and accessible. So for findability, a unique identifier must be assigned to the data, and for accessibility, they must be registered in an accessible and searchable resource, for example, a data archive. So these FAIR principles should apply to humans handling the data, but however, in times of rapidly increasing importance of data mining and machine learning, these FAIR principles should also apply to machines handling the data. I would like to present to you now a format which fulfills these FAIR criteria, being DICOM parametric maps. First, I'd like to give you a quick introduction to the DICOM format itself. So the DICOM format is basically omnipresent in medical imaging. It is the standard in clinical routine, and it's been adopted by all MRI manufacturers. And also there are many tools available for archiving, visualization, and data transfer. It is important to understand that the DICOM standard is not set in stone. However, it's a continuously refined standard to keep up with new developments. And this refinement is done via the mechanism of change proposals. Change proposals, they can be submitted by anyone, and then they will be processed and reviewed by the DICOM community. And if they have been accepted, they will be part of the next edition of the DICOM standard. And also a great benefit of the DICOM format is that metadata can be communicated in a structured way. I talk more about this in detail later. Even as DICOM is the standard in clinical routine, so far it has only found a limited adoption in research. One reason for that is its complexity. So when people start to browse through the DICOM standard, they often put this face because it's just very complicated. Also, in the current edition of the standard, there are many errors and contradictions that still need to be resolved. Sorry. And also, one of the reasons for its limited research adoption is also, I think, merely the lack of understanding its capabilities. And I would like to show you now DICOM parametric maps, which has, I think, a great potential for in the research context. The DICOM parametric map is formally defined as a multi-frame image representing pixels with real-world values. Multi-frame in this context meaning that all maps derived from multiple slices are stored in one file, and this makes it easier to give a spatial correlation to the source data. Real-world values are simply defined as pixel values with defined units. Pixel data of parametric maps can be integer floating point or double floating point value. I think there's a common misconception in the DICOM in the MR community that DICOM data can only be stored as integer values. The reason for this is that when DICOM data are retrieved from the MR scanner, they're usually stored in the DICOM MR image storage module, which indeed can only store integer values. But that's not generally the case in DICOM, so parametric maps also storing data is feasible in floating point and double floating point values. And conveniently, the metadata are included in the definition of a DICOM parametric map. Okay, now we know what DICOM parametric maps are, but how do we use them in practice? For that, Andrei Fedorov and David Clooney generated a tool called DCMQI, which is an open source DICOM parametric map conversion tool, which is publicly available on GitHub. What it does, it converts a data volume stored in an ITK readable, commonly used research format like NERD and NIFTY, and it converts it into a standard compliant DICOM parametric map file. DCMQI can be used as a standalone application or as a software integration. And there are tools which either partially or fully support DCMQI, including 3D Slicer, Cornerstone, MevisLab, MITK, Osirix, or VTK DICOM. Another useful tool is HiDICOM. It's an open source Python library which deals with the complexity of the DICOM standard by providing a high-level abstraction of the low-level details of the DICOM standard. So using this tool, encoding and decoding of DICOM parametric maps is possible in a few lines of code. I mentioned earlier that the metadata are included in the definition of a DICOM parametric map object. Let's have a closer look at that. So the composite context, being the patient and study information in DICOM parametric maps, is just stored like in a normal MR image. The reference series sequence can be used to reference the source data, so by providing a list of UIDs of the source images. Parametric map specific metadata are defined in a so-called real-world value mapping sequence. So this sequence holds a place to store quantities and units, but also derivation details, for example, which post-processing methods were applied or which models have been fitted to the data. However, these derivation details, they are not provided as free text, but what is allowed to go in a DICOM parametric map and what isn't is controlled so-called context groups. And they are in the DICOM standard already a lot of perfusion imaging context groups available. So ranging from T1 measurement methods over tracer kineta models to arterial input function measurement methods. So here you can see as an example of such a context group, the tracer kinetic models. So you can see it's basically a list of contextually related codes. So here with a human readable name, for example, standard TOFTS model, and each of these is assigned a unique identifier. And also in the DICOM standard, we have a description of that code, including a reference. As a remark, private codes are also allowed when there's no standard code to describe a concept. So if you want to fit a model that's not present in a standard, instead you can also use a private code to capture these metadata. The crux of DICOM parametric maps is really that the DICOM standard describes what people are actually doing in their analysis. And we had the crux of DICOM parametric maps, and we had to look in the DICOM standard if this is actually the case. And even if lots of parameters and post-processing steps are available, we also found problems with the current DICOM standard. For example, we found missing entrants. So amongst tracer kinetic parameters, for example, there are lots of parameters that are being mapped that are not present in the DICOM standard. The same applies to T1 measurement methods. Also, for unreproducible description, there's a missing detail level in looking, for example, at automatic arterial input function methods or bolus arrival time estimation. There's not a lot of detail present for these methods. We found some contradictions in the structure. For example, in the current standard, there's at the moment a separation between tracer kinetic and perfusion parameters, even though in the end they're measuring the same parameter. They are sorted in different tables. Some of the definitions were incomplete. For example, there are missing references and partially vague definitions of what is being measured. So DICOM standard, so in order to be used by DICOM parametric maps in practice, we think that the DICOM standard for perfusion MRI needs an update. And from this demand, the initiative of coming up with the DCE-DSC analysis lexicon came up. In order to have a lexicon that can be used as a basis, for example, to update the DICOM standard. And yeah, we're doing this as part of OCP and a task force of almost 15 people. We're an international task force from different fields, from DCE, DSC, and also from DICOM. And we have different backgrounds in physics, medicine, and computer science. We assigned ourselves to the aim to develop a perfusion analysis lexicon, providing standardized nomenclatures for parameters and analysis pipelines, and also to develop a framework for standardized reporting of analysis pipelines. The overall aim is to standardize reporting and perfusion MR analysis and to improve by that the reproducibility. So far we have provided in the almost now first 2-year cycle of this OCP task force the structure of the lexicon, and we filled it with the basic contents. So we found that the scope of DCE, DSC image analysis is just so large that we didn't find it feasible to come up with a complete lexicon all at once. But we designed a structure such that it can be easily extended. So here, just to give you an overview of the structure and the sections we included in the lexicon. So here, give you a quick overview of this. So in section Q, perfusion quantities, we stored all of the quantities that are relevant in DCE and DSC post-processing pipelines, for example, the signals, the constants, and physiological parameters. Then section M, perfusion models, contains all the formats module that provide a relationship between perfusion quantities and the measured and derived signals. In perfusion processes, we collect the methods specific in the context of DCE, DSC, MRI analysis, for example, bolus arrival time derivation methods. And in the section general purpose methods, we included methods that can be used in perfusion analysis pipelines, but they are also used beyond this area, for example, for optimization. Then perfusion, in the section perfusion identities, This section contains relationships between perfusion quantities that can be used to derive one quantity from another, and also often applied analysis pipelines can be stored here in order to avoid reporting duplication. Okay, so what we plan with this lexicon is, after having provided the basic content, is that we plan a dynamically growing inventory updated by the perfusion community. So we plan to do this in regular version controlled feedback cycles. So we want to send out, in fact, the first round of public feedback in January 2022. We do not aim to provide recommendations. So we don't want to tell people how to do the analysis. We just want this merely to be of a descriptive nature. However, we plan to align the lexicon with initiatives providing recommendations, for example, KIBA. So we want to be able to describe recommended pipelines. Coming back to DICOM parametric maps. So one of the applications, or the main applications, is that based on this lexicon, we want to amend the DICOM standard for MR perfusion imaging, but it can also be used for the standardization of other formats and also for scientific reporting. So for example, if you want to use journal publications, you could use this as a reference or guidelines what to report. Okay, in summary, DICOM parametric map allows for structured communication of quantities, units, source data, and metadata. It adheres to good scientific data management in terms of reproducibility, reusability, interoperability, findability, and accessibility. And supporting tools exist along with publicly available sample data sets and reference implementations. Amongst the challenges is that the DICOM standard is and always will be very complex. However, supporting tools, for example, like DCMQI or High DICOM, can lower the threshold of usability. Also, there are imperfections in the current DICOM standard for perfusion imaging, and we aim to overcome these by using the DCE/GSC perfusion analysis lexicon. Using DCMQI as a standalone application at the moment is quite cumbersome because there's no explicit linking between codes and attributes. So at the moment, to fill the metadata, you basically have to go manually through the DICOM standard. However, this can be taken care of by software solutions in end-user applications. To summarize, so with all the challenges to overcome with DICOM parametric maps, say it is a very useful format in the research context, and with the perspective of data management, I would say it's currently better than alternatives. And with this, I would like to thank you for your attention and happy to answer questions.
Thank you very much, Anna. That was great, really interesting. And interest of time, we haven't got very long for questions, so I will encourage people to go over to the attendee platform after this talk, but I'll just ask one quick question that's come in from Simon Duran. He said that I'm a bit concerned about the statement that the DICOM standard is full of contradictions. While some may exist, as various committees work hard to eliminate them, could Inna give some examples of what she means here, please? Yes, it's in the Q&A.
I was just busy stopping my
Sorry. Simon's just a bit concerned about the statement that the DICOM standard is full of contradictions, and he's saying that there's various committees working hard to eliminate them. Could you give some examples of what you mean by
I meant it specifically for the perfusion context. So yeah, I had a slide was coming up, for example, missing entries, and for example, one contradiction would be that there's a distinction between perfusion parameters and tracer kinetic parameters. I would say that that is a bit of a contradiction, at least, yeah, because I think in the end, it's quantities sorted in different tables. However, they're basically the same quantities, but measured by different modalities. So example, even if it's measured by DCE or DSC, still the same quantities are measured. So that's what I would describe as a contradiction in that sense.